Yes. Yes, there is a person. So,
Well, I think we're over time already. So.
yeah, with Leo, I'm tempted to say if he takes longer with his
Setup.
main camp, we just let him run until, but I mean,
Okay.
we can ask. Right. Okay. Yes, we are. Gosh, it's empty.
Yeah.
That's such a good room.
Interesting.
Is it still afternoon, I suppose?
Yep. 2 minutes late.
All right. Good afternoon, everybody. I hope you're here for Cfrg. Right. Please take your seats, finish your conversations. Right. I didn't ask for agenda, but I suppose it doesn't ask. Yeah, but there's no way of projecting it.
We didn't project the agenda.
Yeah, that's right. Okay. So Cfrg is part of IETF, so we abide by the same rules as IETF, so not well applies. I hope that's not the first time you've seen it this week. I think we have JavaScript, we have note takers. You might notice that we have, just use this one. So we have a new co-chair, Nick Sullivan, sitting next to me. Kenny is absent. We also have a Cfrg secretary now, which is Stanislav, who's going to help us with timekeeping today. Very quickly, document status. We managed to publish 2 documents since Prague. We have rekeying still in RFC editor's queue. Argon 2 is getting really, really close to being in IRSG review and being approved. Spec 2, Kenny still need to have a look at this. In the list of active documents, you can see we actually have accepted quite a lot of documents. We have 8 documents at the moment, so quite a lot of work, but some of them in early stages. Luckily, we're not going to publish them all at the same time. So, chairs rely heavily on crypto review panel, which was formed in September 2016. The purpose of crypto review panel is to help review documents for Cfrg, whether they are just beginning their life cycle or are in the research group last call, as well as helping security area and independent stream to get reviews of crypto algorithms. There were lots of very good reviews done. Chairs will be relying on the crypto panel to help with reviewing PAC submissions. In order to do that, we just, chairs just realized that the term of existing members already extended by 1 year would have ended in September, so we extended it till the end of the year. Also, we are reopening nominations, so we're looking for new candidates. So if you know somebody who will be good, whether they have more academic experience or even industry and protocol use experience, we are looking for both. Please submit nominations by September 1st to Cfrg chairs, and self-nominations are very welcome. So don't be shy. One of the main sort of big task that we started last time is PAC selection process. We have 8 submissions. Nominations ended in June. We got preliminary information from all submitters. The aim is to hopefully find more than 0, but recommend 0 or more PACs to as Cfrg recommended documents. Stanislav is helping out with organizing the process, and he will have a talk at the end about the current status, the current submissions. If people have suggestions for chairs, how to, which kind of questions to ask to help us decide, please contact us either at Cfrg chairs or talk to us privately. And on that, I think we are starting. Yes, my apologies. We are 2 minutes late, but we'll start with the first presentation, which is Richard.
So this is about the HPKE draft, which is the current slightly suboptimal name, hybrid public key encryption, in that it is encryption that combines an asymmetric operation, public key operation with an AEAD. So this is now draft IRTF, Cfrg, HPKE. We submitted 00 just before the draft deadline after having a successful adoption call. So let's get started. So made a couple of changes between the last individual version and this one that were kind of cleanup oriented. Sorry, I don't have the monitor here, it's not working. So the main change in this draft was to kind of clean up the logic. We had a diagram like this in the last deck when we presented this in Prague that had a lot more boxes. And basically we've pulled all of the logic into this encryption context creation function, which gets a bunch of parameters from a setup function depending on what mode you're in, and then generates a context and a key and a nonce that you'll use for encryption operations based on that context. Thanks. So in the earlier draft, in the individual draft 00, we only had the one mode where you just encrypt to a public key, and in 01 we added these other modes where you can encrypt where you can encrypt to a public key and also authenticate that the sender has a given symmetric secret, a PSK, or that the sender has a given private key, this auth mode. One of the things that this consolidation gave us was that we can now have a mode where the sender can prove both of those things. They can prove both that they hold a given symmetric secret, a PSK, and that they hold a given asymmetric private key. I don't know how much use that is. I don't think there's an immediate use case for that, but it just seemed like for the sake of completeness, we have the capability. Why not just add the mode? One of the questions here I'll get to in a second is whether we think that's worth it. So that's the major technical change in draft 00, this draft. Otherwise, it's pretty much the same as the earlier versions. Since the last IETF, we have now 2 implementations. I've done one in Go, and Dave Cridland has done one in Python. These kind of do orthogonal, or are good at orthogonal things. So Dave is really nice because the pseudocode that's in the spec is kind of Python looking, and Dave's is in Python, and hews very closely to the pseudocode that's in the draft. So it's very easy to understand that way. My Go implementation is a little bit more completeness oriented, so it covers all the Cypher suites that are in the draft right now, and as of yesterday, includes Psych as a kind of a demonstration proof case that we can integrate a post-quantum chem, because one of the things we did in 001 was like change from a DH orientation to a chem orientation with this idea that we could use post-quantum chems there. And we have at least kind of empirical code-based validation that that's possible. I haven't had this reviewed by anyone, maybe using it completely insecurely, but it at least like compiles and runs and passes tests. And it was actually a pretty small patch. Like once we had the framework for this set up, it was really just that little bit of glue code to get the post-quantum chem patched in. So I think it's kind of a promising sign for the ability of this construction to evolve forward into a post-quantum world. There was some discussion on the mailing list and during the adoption call about some other things one might ask for out of this construction. And I think that we discussed in the list, and I think that we kind of got to pretty good consensus on not addressing some of these things right now. So forward secrecy is kind of not a sensible thing to address here. That's kind of a property of the key that you are encrypting to. So we're going to build a construction here for encrypting to a public key, and then forward secrecy properties depend on how you rotate that public key and things like that. So the idea is that we're building up something here that you can then embed into other systems that provide things like forward secrecy. MLS, for example, will provide forward secrecy and PCS properties. KCI resistance. Honestly, I'm not, I don't feel like I deeply understand this, but some other folks can hold me honest on this. I think all of the words in this bullet here make sense. If you have a one-round chem-based protocol, we can't resist that style of attack. You need something like digital signatures from the sender to make that possible. And I think the feeling right now is it doesn't make sense to add in that extra machinery to get that property. Again, if you need that property, you can add it in at higher layers than this. Finally, post-quantum, I don't think it makes sense to put that in the spec right now. As I said in the last slide, we kind of demonstrated that it works, so it's good to have that validation that it's possible. But I don't think it makes sense to like define Cypher suites that are for post-quantum chems right now, because we don't have anything that's kind of ready to have a code point quite yet. So that's kind of the state of the art. Wanted to frame a couple questions for the working group because, now that we've got it adopted, we can start thinking about how do we get it to the state of completion. Dan, you have a question? Comment?
Dan Harkins. If the sender reused his key pair and then did DHKEM, then the context would produce the same secret and the same nonce, right?
No, because there's an ephemeral key pair that's generated. In DHKEM case, there's an ephemeral key pair that's generated that is fed into the context that generates the key and the nonce. So that each encryption has fresh entropy.
It's impossible to do static in the DHKEM?
Chris, you're nodding. Can you go to the mic maybe?
That's okay. Nodding is fine. Okay.
Yeah, there is no mode where everything is static. that addressed the question, yeah. Yeah, so thinking about now, like, what do we need to do to get to completion here? I think the major question in my mind here is this draft trying to do too much? There's all these modes. We talk about how you authenticate the sender in these various ways. We talk about how you do multiple encryptions off of a single context generation. I think the feeling of the authors was that those things were useful. We had kind of demonstrated use cases from some of the prior art with libnacl and things like that, where people were making uses that have that same general shape, so it made sense to cover those in this doc. But I could understand if people wanted to slim this down and have a more straightforward doc to review and do analysis on. People have thoughts, comments on that? Jonathan?
Relaying from the Jabber room. Tanya Lang, it depends on how they define ephemeral. as one-time or short-term?
Yeah, I think that's, I think in the sense in which we mean ephemeral here is that the key pair is generated for the purpose of a single encryption. So it really is one-time use. Yeah, Adam.
Adam Langley. So if you're worried about doing too much, I think the example of noise might be useful. If you've seen noise, which is a framework for two-party communication protocols, which has generated like Noise Explorer, which generates like formal proofs of sort of like many of these things and tells you exactly what properties you get and so forth. Like that, I think, was useful and demonstrated that you could do something worthwhile with an overly general system. So if you go there, I think like being general is good. But this is the IETF, and obviously there have been plenty of protocols that have been over general, and that hasn't produced any positive effects.
So when you say go there, what do you mean?
I mean, if you start adding, you've got 4 modes now. I'm sure there are others in your mind and so forth. I guess I'm saying like look at sort of Noise Explorer as I think a high point of what you can do with a more general framework. And if you don't want to do all that, then like trim stuff away.
I see what you mean. Yeah, I think kind of analysis was the other big thing we're waiting on here. I think the INRIA team at least are looking to do like a single composed analysis of this, much like they did a single composed analysis on TLS, from which the verification of the modes kind of falls out of special cases. I think this is still a small enough target that that's a reasonable thing to do. The logic is fairly well consolidated, and so I think of this as kind of orthogonal approaches to the noise compositional approach and Noise Explorer approach, but I think this is still reasonably simply composed to make that sort of analysis possible. But of course, I don't do the analysis, and so I can't really speak authoritatively to that. Yeah, Riyad.
Riyad Wabi, if you were removing things, what would you remove? Like you say, are we doing too much? There are 4 options. If you had your druthers, would you remove any of them?
I think the simplest, the thing that could be removed that would make the most impact is the modes in which the sender is authenticated with an asymmetric key, because this requires this auth encap, auth decap thing, which is only, like, I don't know if that really extends to any non-DH chems, and we just kind of define it ad hoc for chems. Now that, I mean, that is, if you're looking for like feature parity with the Box API, I think that feature exists there. So there's some benefit to having it there, but it does introduce some additional complexity into the spec, and it's more optional things to keep around.
As one more thought, would it be reasonable to consider removing the unauthenticated case? Arguably, there's no reason to use an unauthenticated count. So.
I'm not sure it would streamline things much.
That's fair. That was what I was suspecting. So yeah,
I mean, it might streamline things if you were going to remove, focus in on only the PSK case or only the authentic asymmetric case, right? If you were going to do one of those, then you could cut out some stuff related to the unauthenticated case. But if you're going to have both of those and you're going to have some optional stuff on both sides, then the unauthenticated case kind of emerges as a special case. Where, so yeah, I'm not sure that simplifies it much, but I appreciate the instinct.
Thanks.
Yeah.
Hi, Joe Salaway. If this were a working group, I would say like we would really want to take out things we didn't have a use case for as a research group. I'm maybe less inclined to that, but I think probably if we can trim stuff out, it would be better, both for the amount of work involved in improving it. But as you say, some things may just fall out and it may be a non-issue, but it kind of helps to have less is more.
Yeah, so. I appreciate that. I mean, personally, my feeling is that we've got a reasonably consolidated set of logic. The thing that honestly makes me question, the aspect of the I question most is the both mode where we have both a PSK and an asymmetric keeper, because there's nothing in the art that does that right now. So it's not clear that there's a case for that, although it may be used. I'm still writing my MLS slides. There might be an application for that in MLS, but it's not in any of like the open source software now. So that's the thing that it's least clear that there's a use for, but at the same time, it's basically zero cost because all the machinery is there for the other 2 modes. So So my inclination is kind of keep things as they are, but I'm open to arguments if people are really concerned about complexity here. Otherwise, I think Karthik and company, and welcome other analysis, I think Karthik's ready to kind of proceed ahead with doing verification on the full construction. Okay. And the last issue I had, which naming came up on the list and people didn't like HPKA, so I figured, I got a couple minutes left to give people a chance last chance to come up to opine on alternative names. This was the best that the authors came up with, and so my proposal to the room basically like, let's call it HPKE or let's call it cashew and let's consider the question done. I would propose we stick with HPKE, but if someone wants to stand up for the alternative, be my guest.
Yeah, I love cashews. I don't really care for this name. Let's just stick with HPKE, I think.
Okay. Was that a +1 from Adam? Hey, provide me an expansion and we're on. All right, that's all I got.
Good afternoon, dear colleagues. Stanislav Smyshlev, CryptoPro, and this is a very short overview about MGM mode, which has been standardized in Russia as an AID mode in 2019. The description became available 2 years ago, and the motivation for the development was such that there was known security issues with GCM, and GCM was not so widespread, so we have a chance to make something new. But the designers were late to Caesar contest, so it was not nominated. This is only an informative talk without any plans for adoption, at least now. So the scheme is on the slide. Basically, the encryption process is counter mode, and the authentication process is kind of like GMAC from GCM, but with a new secret value for each new block of data, and with separate counters, with separate nonces, and with additional operations at the end of the process. So if we consider the functional properties that are satisfied for GCM, we may see that except for the sixth one, they are satisfied for MGM, and with the sixth one, it is half satisfied, because if we have our nonce beforehand, then we can make these precomputations for authenticated data. So the difference is that for GCM we don't need nonce to go with authenticated data, and for MGM we do. So there are some protections against length extension attacks with mixing in lengths at the end of the process. And protection against predictable collisions of counters due to separate initial values of counters and different processes of increment. So, and if we have a very brief overview of attacks on GCM, we may see that for all these kinds of attacks on GCM, we may see that MGM has some countermeasures to protect against them. Encryption of things here and there in the authentication process, usage of separate and distinct secret values for each block during authentication operation to counterfeit Sarnin-like attacks. We have some security bounds obtained, and they're present in this paper shown in the slide. And the last slide, very short comparison with our AAD modes. It can be seen that, but for GCM, it is right that none of the modes is better for all properties. So there is a certain subset of properties for which MGM can be preferred. So it can be used for some certain applications when its properties are desired. That's all, and there are some backup slides so that you can use if you want some additional operation.
One very minor detail. GCM also has the interesting property that you can...
Sorry?
Scott Fluor, Cisco Systems. The GCM also has the additional property that you can actually implement it so that you can start encrypting before you know the additional data, even how long the additional data is. A very minor detail, but yeah, it's there.
So yes, thank you for the comment. So in fact, yes, GCM in fact has a lot of good functional properties, and not all of them are enumerated in the slide. And if you'd like any comments about how some of them are or are not satisfied for MGM, I'd be happy to comment.
Hi, Yovnir. So it seems like it has some real advantages over GCM. So why are you which makes me that it would be better, well, in some respect, to using ASGCM in, say, TLS or IPsec. So why are you not asking for adoption?
So I'd like to announce here that I'm not the designer of the MGM, so I was the guy who was who conducted some part of analysis of it, so I can't comment all design ideas of it, but the idea was to take all the best from GCM, but to fight its weak points. But of course, it's slower if to talk about implementations without parallelism, but if you implement this in parallel, you can address each block one by one at the same time in parallel mode.
Hello. My question is really about the security comparison to ASGCM. None of the attacks you cited actually, the probability one, none of the attacks you cited break the break the security of ASGCM. The forgery probability is exactly what it says on the slides, and it looks like MGM is actually slightly worse. From that, it's also less efficient. And what are the properties you're gaining with MGM over AES-GCM?
So thank you very much for the question. Yes, in fact, in addition to the countermeasures against certain attacks on GCM, MGM also has better security bounds if we consider authenticity. They are on this backup slide, so you can see that for some typical values of lengths and the number of blocks, MGM is better. And also in some positions when some forbidden actions like nonce reuse happen, it has a little less impact of security. So, of course, the comparison of the modes can be only by tables, but if we see the authenticity bounds, see for which cases MGM looks better, we may see some applications when it can be preferred. But I have nothing against GCM, in fact. It's just information about modes that is slower in some sense, but that has some stronger security parameters in other sense. And I would add that, for example, for confidentiality, MGM has a little weaker formally security bounds because of the fact that it has to deal with that additional bit to split two counters for encryption and for authentication. So this presentation was not about giving all the details of MGM, and I think I don't have any time left, but I'll be happy to comment, etc.
One last question.
Yeah, so, but on your backup slide, it looks like that's the reverse of this slide. on the backup slide, you have GCM performing better than MGM. So what's the difference in the parameters here?
For conditionality, better than GCM a little, and for authenticity, MGM is much better. Please refer to the authenticity slides. Thank you.
So, hello everyone. I am Shoko Yonezawa, and it is my first IETF, and I'm grateful to give a presentation here. Today, I will talk about pairing-friendly curves. So first of all, I give a brief overview of this presentation. So pairing-based cryptography, which I will explain later, is getting widely used, and the security evaluation of pairing-friendly curves, which realize pairing-based cryptography, has been changed due to the attack proposed in 2016. So introducing secure pairing-friendly curves after this attack are required. So to solve this problem, the goal of our draft is to show the latest security evaluation of well-known pairing-friendly curves and to show the new parameters for pairing-friendly curves with each security level, namely 128-bit or higher. So our draft is strongly related to the existing RG items. B-area signature scheme is one of the examples of pairing-based cryptography, and B-area signature scheme uses the Hassing-2 pairing-friendly curves specified in Hassing-2 elliptic curves. So thankfully, these drafts referring to our drafts. So let me explain the more details about pairing-based cryptography. Pairing-based cryptography is a kind of elliptic curve cryptography. The main difference is it utilizes the special map called pairing. So, and thanks to the property of pairing, the cryptography with more functionality can be realized and getting widely used. Here are the examples of standards and implementations of pairing-based cryptography. For example, so we can see you can see that you can see ECDAA specified by TCG, FIDO, and WCC, and Intel SGX EPID for the remote anonymous attestation, which realizes the attestation in a privacy-preserving manner. Another example is BLS signatures, which enable signature aggregation and realizes the compression of certificates, the signature of certificate chain or the signatures of blockchain and so on. And more, in addition, the potential schemes are proposed in the research paper and can be realized in the future. So, like standard elliptic curves, the pairing-based cryptography requires underlying elliptic curves. That is, the elliptic curve cryptography like ECDSA, ECDH, and EDDSA require underlying elliptic curves defined by NIST, Cfrg, and Cfrg. Similarly, pairing-based cryptography like BLS signatures require pairing-friendly curves. And like elliptic curve cryptography, the security of pairing-based cryptography is estimated by the security of pairing-friendly curves. So let me explain what pairing is. So this slide contains the equations, but they appears in only 2 slides. So okay. So pairing, also known as a bilinear map, is a map from the group G1 and G2 onto the group GT, which satisfies this equation. In general, group G1 and G2 is a subgroup of elliptic curve groups, and GT is a subgroup of multiplicative group of finite field. So there are various pairings proposed, and optimal 8 pairing is considered to be most efficient and popular. To compute pairings efficiently, pairing-friendly curves are introduced. Example of pairing-friendly curves include BN curve, BLS curve, and so on. So, and BLS curve varies in their embedded degrees. So, and the pairing-friendly curves vary in their key lengths, which determine the security strengths. So we call the pairing-friendly curves like so by their curve family and key lengths, such as BN254, BN256, and so on. So how can we evaluate the security of pairing-friendly curves? As shown in the previous slide, the pairing-friendly curves contains 3 groups. G1 and G2 is chosen by the elliptic curve groups. They are based on ECDLP, elliptic curve discrete logarithm problem. By contrast, GT is chosen by a multiplicative group of finite field, so they rely on finite field discrete logarithm problem. So, so we have to consider. So, in the general standard elliptic curve cryptography, we can only consider G1, but in pairing-based cryptography, we have to consider both G1 and G2 and GT. And the complexity of ECDLP is known as exponential, but the complexity of GT is known as sub-exponential, so we have to consider the difficulty of GT. In 2016, the algorithm to solve FFDLP was proposed. So at first, there. Okay. So due to the attack, the security level of all pairing-friendly curves has fallen. So we have to consider the new security evaluation of pairing-friendly curves. For example, after this algorithm, BN256, which are regarded as 128-bit secure so far, are fallen to the 100 bits of security now. So introducing new parameter for 128 security level is required. So in our draft, we select the parameters for each level of security in terms of their security and also the efficiency when implemented and how wide they are used now. Based on this evaluation, we in our draft, the 128 bits of security and 256 bits of security are introduced. Our opinion is these two security levels are sufficient. So we are wondering what 192 bits of security parameters should be defined. So candidate curve is BLS24 for family, and several papers for this security level are proposed, but no implementation are published so far. So our question is, how can we treat 192-bit parameters? To answer the question, here I give one fact. In USC NSS suite, the security parameters for asymmetric cryptography are said to be 192 bits of security. But on the other hand, the statistics says that the TLS servers, in the TLS servers, supports 256 bits of security rather than 192 security. So based on them, our consideration is we can select only 128 bit of security and 256 security. So here is the history of our draft. We after the initial submission, many comments are posted in the mailing list and revised according to them. So if you're interested in, we proceed our process. That is all.
Yeah, we'll take one question, and after that, yeah, really quick, we're behind.
Riyad Wabi, sorry, real quick. So I emailed you about this, but maybe it's a question for the wider audience. One of the major applications of pairing-based crypto, as was mentioned in the slides, are for pairing-based arguments, SNARKs. BLS 12381 is designed for that purpose. none of the other pairing-friendly curves being proposed are? Well, no, the BN curves are, but let's ignore those. They're too low security. So the question is it worthwhile to also define 192-bit or 256-bit argument-friendly, pairing-friendly curves? It may be no, because already the prover's work in Snarks is preposterously bad, and so like 192 or 256 bits of security is like unbelievably slow.
So it is not our goal to specify variety, many curves. So we have to consider the multiple parameters are good, but so many parameters are not for implementers to implement, because they are confused which curve to be implemented.
Yeah, that's totally fair. Like I said, I'm not aware of any applications that really need that high of security, but it's something to consider, because it may be that in 2 years everyone wants to do it, and then, oh no, we need to add a curve. So for example, if no one, as far as I know, no one is actually using BLS 48581. That's just like some curve that, we run on our laptops to benchmark it or something, right? So I don't know, maybe there's a BLS 48587 that is, that would be reasonable to use with pairing-based arguments, in which case maybe it would be worthwhile to standardize that instead of 581. I don't know. Like I said, I don't actually know if people are using 581, and I wouldn't suggest that we get rid of it if they are, but if they aren't, maybe get something that has both.
Yeah, let's keep this on the mailing. Let's move this to the mailing list.
Relaying from Jabba.
Really quick.
Okay, apparently there is another option, which is optimal TNFS secure pairings on elliptic curves with composite embedding degree. And there's a link to a paper if anyone's interested.
Great, let's discuss that on the list. Last question.
This is real quick. I just wanted to thank you for bringing this work to the CFRG. I think it's very important. We have a use case for it. We're interested in identity-based cryptography, and we're going to need some standardized curves. So I'd like to see this go forward.
Great, and before we move forward, if it's great to see if anybody else here in the room has applications of pairing-based cryptography that they need to. So rather than a hum, if someone has an application, please raise your hand. Okay, so not many, but a few. Thank you.
The next presentation is going to be remote, and I think chairs need to be in the control of the slides, but...
All right, Leo, we'll put you on. We can't hear you.
Can you try to present again? And we'll see if it works now. If you struggle, we can swap presentations. We'll give you another chance later on.
Better?
Yes.
Okay. Good old leave the page, open the page again. That's the trick.
Great, we can hear you.
Ready when you are.
We can hear you, and just let us know when to advance the slides.
Okay. Let's go. Yeah. So thanks a lot for allowing me to present my work. I'm Léo Perrin. I'm in Paris right now. I'm a postdoc at INRIA. And what I'm going to talk about is this paper that I authored, which was published at TOSC, the Conference for Symmetric Crypto, and its consequences regarding to RFCs. So I'm going to tell you what the result presented in this paper is and why it is inconsistent with the claims of the designers of said algorithms. Next slide. So I'm going to go quickly over the general context of this work. Well, what are standards, but obviously I'm not going to spend too much time on that. and what are S-boxes. Then I'm going to talk specifically about the S-box of these two algorithms, and finally tell you why I don't like this S-box. Next slide. Next slide. So the lifetime of an algorithm can be represented in this way. Next slide. So you have these three phases: the design, the analysis, and the deployment. I'm not going to remind you what the actors are. I believe you're all familiar with them. Next slide. So when we design a new algorithm, we come up with a scope statement and we write down its specification. And much more importantly, we make choices during the design and we justify them. So we explain them and we justify them in the specification. And we also do a first security analysis. Next slide. So we put this all in a publication, and then the public, so the general academic community, we try and break said algorithms. Next slide. If they manage, we put it in the trash. If not, next slide, eventually the algorithms are trusted and they are standardized. And then they will be implemented in actual products until a new attack is found. Hopefully not, but perhaps. This is the ideal world, and indeed it actually happens in this way in many cases, but not always. Next slide. Sometimes we have an algorithm which is designed by unknowns, which is standardized right away. And we don't have the publication with all the explanation of all the design choices in this context. And as you can see, there is no trust anymore on these slides. Next slide. The problem we have in this case is that there could be hidden defects in the algorithm. Since for the analysis, we cannot leverage all this public information, all this explanation about the design choices, etc., we could overlook some aspect of the design and miss a flaw. The flaw could be intentional or not. It could be a perfectly honest mistake that we still cannot see because we don't have this information. Next slide. An S-box is a very popular component of symmetric algorithms. It's usually the only nonlinear one. So an S-box is a small nonlinear function which is so small that you can specify it using its lookup table. So typical size are 4 or 8 bits, and they can be designed in very different ways. So this is a survey I made during my PhD. There are many different structures. I'm not going to go over them. Next slide. How do we justify the choice of an S-box? We can just look at what the designers of the AES did. So this page, you can see, was taken from the document whose URL I put in my slide. It was written by the AES designers. And as you can see, they have first a clear design goal. So they want their S-box to be invertible, etc. Then they explain the motivation for the specific solution they chose. So it turned out there was a paper explaining that the inverse was very nice. So they went with that. They also identified a possible issue with this approach, which is that the algebraic expression could be too simple, and this could be an issue. So they found a way to remedy that. And then finally, they described the process they used to choose the actual S-box of the cipher, the one they actually used. So this is how it should be done and how it is often done. This is not how it was done for these two algorithms. Next slide. Next. Yeah, thank you. These two algorithms, it's the hash function Stribog and the block cipher Kuznicki. Hash function and the block cipher, both are standards in Russia. Both are RFCs, although not from the Cfrg. The chairs insisted on that. They are from the independent stream. They were designed by the TC26 along with a company, and the TC26 is a committee which is supervised by the FSB. What matters to me for now is that both of these algorithms use the same 8-bit S-box, which they denoted by. Next slide. Over time, so first, these algorithms were published by the GOST, so the Russian Standardizing Agency, and as RFCs. After that, next slide, we looked at them with my then colleagues from Luxembourg, and we found two decompositions of this S-box. So we found two ways of writing it, which was very puzzling for us. We found the first one, and then we found the second one, which was completely different. So the conclusion of these two papers was that this S-box was very mysterious, And there was more to it than we could find. After that, next slide, it was standardized, Cfrg was standardized by ISO. After that, I found the final decomposition. So that's the one in the paper I mentioned on my very first slide. This is the final decomposition because it explains the other two. The first two decompositions are just side effects of this one, and it's much simpler. So at that point, problem solved. That's how they built the S-Box, or so I thought. Next slide. The discussions are still ongoing at ISO. So they were supposed to standardize Kuznechik, but they decided instead to postpone the decision for 6 months until they had the time to figure out the consequences of my work. And next slide. They would have to take a decision in September. So I mention ISO a lot here because actually they were like a side channel, as you will see. Next slide. So why do I not like said S-Box? Next slide. That's all we know about them. This is all the information that was provided by their designers, the lookup table. It's all you need if you want to implement the ciphers or the cipher or the hash function. But if you want to evaluate its security, it's not sufficient. Next slide. However, during discussions at ISO, the designers of Cfrg and Kuznechik did provide them some information. At ISO, it's behind closed doors, but this information was leaked. So I have put the URLs on my slides. And in these documents, you can read what is on the slide, namely that the S-Box Pi was obtained by pseudo-random search. No secret structure was enforced during its construction. This is wrong. What I have proved in this paper at TOSC was that pi was actually described by these very simple equations. So the designers defend themselves now, saying basically what is written on the second block. At the same time, it is obvious that for any transformation, a lot of representations are possible. Basically, what they say is that, yes, pi has this structure. It's impossible to deny. You can just check it. However, had they picked the next S-Box in their generation process, I would have found another structure in it. This is wrong. Next slide. To see why it's wrong, we need to come up with a sensical definition of simplicity that we can still evaluate. So that's exactly what we did. There are about 2 to the 1,684 8-bit permutations. So in any given language, you're going to need at least 1,684 bits to be able to represent all of them. And most of them will have a very long representation. The number of S-boxes with a short representation is at most the number of bit strings of this length. Next slide. And this is an implementation of pi. It's C, not super readable C, but perfectly compilable C. And it's only 1,155 bits long. Next slide. In fact, we invited the Code Golf community at Stack Exchange to come up with the best implementations they could find, so the shortest. And one of them, found by one Odsan, is only 624 bits long. Next slide. The probability that for a random S-Box, so one that you have obtained via a random search, is that simple, meaning that it can be implemented by a program this short, is at most 2 to the minus 1,000. And that's assuming all bit strings correspond to the AMD 64-bit code implementing a permutation. It's not. It's wrong. It's not a tight estimate at all. It's an upper bound. And this upper bound on the probability is 2 to the minus 1,000, which I hope you will agree is very low. Next slide. So where do we go from here? Next slide. This statement by the designers that they had not enforced any structure in their algorithm cannot be reconciled with the shortness of their implementation, of the implementation of their S-Box. It is not possible to generate an S-Box at random and obtain in the output something with this simple a structure by chance. The probability is so low that it's beyond negligible. We're happy with 256 bits of security. Here we have 1,000. Next slide. I think what this means is that the designers have provided misleading information for the cryptographers who wanted to analyze their design. At first they said nothing, which is not the best practice, and then at ISO they provided wrong information. Next slide. I don't need to tell you how hard it is to do the security analysis of an algorithm. Even if we have all the data in the world from the designers and all the goodwill from the designers, if we have not just an absence of information, but wrong information, it's even more difficult. And I can't think of any good reason to complicate further the task of external cryptographers. Next slide. That's why I think the designers of these algorithms cannot be trusted. These algorithms cannot be trusted, and why I believe they should be deprecated. I don't think we want to have RFCs for those. And that's it for me. Thank you.
Okay, any questions?
Well, I agree that we should. Baker, I agree we should stop using them, but I would really encourage people to find out how they. I assume that there's some jiggering going on, and I would really be interested to see how it could be exploited, which will be the next part. But we don't need to see the exploit in order to stop using it.
I agree.
We'll cut the line here.
Okay. Yovner, so I guess you don't want me to write Kuznetchik for TLS thing. Okay, never mind. The real question is, you're saying that ISO is standardizing it and they are making the decision in September. Suppose they do, who needs to use this? I mean, what does it mean that ISO is standardizing it?
I encourage you to watch a talk given by Atul Luix at Real World Crypto this year, where he talks about the impact of an ISO standardization. In this case, he was worried about Simon and Speck, the ciphers from the NSA. But an ISO standardization can have more consequences in the sense that it could be enforceable in some cases to use these algorithms, like to force people to use these algorithms, if I'm not mistaken. But Atul explains it well in this real-world crypto presentation. It's on YouTube.
Russ.
Hi, Russ Housley. I am a little concerned about the things you've raised here, but I also feel like we've heard this story in the 1970s when Marty Hellman said, hey, there's something funny with these DES S boxes. Don't know what it is, but it doesn't feel right. There's a symmetry in there. And then it turned out that that symmetry was put there to defeat differential cryptanalysis. It just wasn't publicly known yet. I don't know if that's what's going on here or something else, but you don't know. You just know something smells funny, right? Is that
yes, there is a big difference also. As far as I know, in the case of the DES, the NSA never said anything. That's what they tend to do if you talk with them at conferences. They don't say anything. In this case, they said something which was wrong. I believe that's the big difference.
I agree with that. The difference was the ISO registry didn't exist back then as well.
Stanislav.
Stanislav Mushlev. Leo, really, many thanks for your work. I am not a designer of the algorithms, but I work in a software company in Russia that uses these algorithms in the software that is provided for government and its requirement. And so I'm really very proud of you that you're spending so much time on analyzing this, because really an algorithm that is used must be analyzed thoroughly. But I have to mention two issues with the slides. First of it is that the absence of public information before standardization is not fully correct. Even in your paper, you cite the papers of 2014, and for Cfrg, moreover, it was a public contest. I agree that it was not as public as it could be if it will be worldwide, but at least it was public with some prizes, and a lot of people outside of Russia participated. But in any case, I totally agree with you that any analysis and currently should be done. And about your point about the conclusion. In fact, I really want you to find some time to continue your efforts, because any concerns and any questions about the structures must be answered. But if to be honest, if you would find something like Ferguson and Shumov in 2007, when there was a statement like, if the designers knew such discrete logarithm, then such an attack can be mounted. Then if you had some such statement, then the question about it could be stated in Russia, could be stated in ISO, everywhere. But if you just say that there are some concerns, and even in the paper that you cite, the paper of Filiol, the author, Eric Filiol, says that there are quite different things, and the cosets is the only word that is in common. So you say that there are some structures, and some another structure can be used for exploit, but they are really different structures. It's like saying that when you use DLBG with elliptic curves and it has backdoor, and then ECDSA has a backdoor too. So of course you have very good results, and I want you to continue it, but they don't show anything about attack or backdoor now. But of course you should continue your work, and it will be very good. If you will find some attack or some method, I will be happy to discuss it with you, and maybe you'll. I hope that nothing will be found, and if not, then it's just a concern, a question why such property were not disclosed, or if it was known by designers. But there's no reason to say about backdoor or some attack. It's just some properties.
So I never claimed I had an attack. I actually was always clear, at least in the paper, I hope it's clear, that I do not have an attack that exploits these properties. I do not. That's a fact. And yes, there has been some external cryptanalysis of these algorithms, especially Stribog. There was indeed the Stribog competition, but at the time, the cryptographers could not also check the impact of the structure of the S-box they had, the designers chose. They could analyze the cipher from its specification, but that's all they had to work with. And I think it's a bad thing. I think they should have had all the information at hand from the get-go. I shouldn't have to spend 3 years finding it by hand. And also, so yes, indeed. So I didn't talk about it in this talk because I didn't have time, and because it was perhaps it would take me too far. But the fact is that this S-box interacts in a non-trivial way with cosets of the subfield. So it interacts with additive cosets, which is exactly what Filiol used. So it's not completely different. Half of the pattern involves additive cosets, which is exactly what was used in the backdoor of Filiol and Bagné. The other half is indeed multiplicative coset, which is different. That's also a fact. At the same time, the designers of Stribog also did not disclose the way their linear layer was built. And the way this linear layer is built is using matrices with coefficients in the finite field, and it's the same finite field as the one used to design the S-box. So the linear layer also interacts in a non-trivial way with the subfield and its multiplicative cosets. And that's something we don't understand right now. So I cannot exploit this for an attack. Again, I want to be very clear on that. I do not have an attack against the cipher. But it's more than just finding a specific structure and not liking it. I have good reasons not to like it. And one of these reasons is because, again, it interacts with the subfield in a way which we don't understand so well, and we don't know how it interacts with the linear layer. But the main reason, which has little to do with the specifics of the property, is indeed the fact that the designers did not disclose it. What I have established, what I have proved with this code golf thing, is that it had to be put there by someone. Such a structure does not happen by chance. I don't know who that someone is, I don't know why, but it was put there on purpose.
We've got to move on to the next presentation. We're well behind. So is this going to be a very short question, or is something that can be taken to the list?
most of the comments were made by previous commenters, so I have just a couple of notices. One is that I see logic leak in the statement then if something can be effectively presented in computational meaning, it should be not taken by chance or by any other things. That's I do not see logic in that. Another one coincided with that. I would like to have a great thank to the presenter to the bringing attention to the possible effectively computational representation of the S boxes. The developers of the ciphers are very thankful to you for that and for the bringing the attention of code golfers to the having more efficient computational representations, which is extremely important in constrained environments. Thank you.
Okay, thank you. And Leo, thank you for your presentation, unless you have...
I got it, okay.
Okay, great. Riyad? Let's try to keep it fast so we can...
Okay, this is a quick update on hash to curve. One of the updates appears on this slide. I'm a new author, and so is Armando. Armando's put in a ton of work, so he's not here, but thank him. In general, we can think of hash to curve the way that we're describing it in the document in kind of 3 steps. The first step is hashing from an arbitrary string to an element of a finite field. The second is going from that element of the finite field to a point on the elliptic curve, and then the third is clearing the cofactor for any curve that has a non-unity cofactor. And so the goal is to make all 3 of these steps constant time. So in particular, there is no hash and test or hunt and peck or however you want to call it in this draft. That is a conscious choice. We don't think people should use it. There are fast algorithms for essentially every curve. So let's talk a little bit about the changes to hash to base. So we've added in this new draft explicit security requirements. This means how you choose the hash function, how many bytes you extract from the input string. The goal here is to get collision resistance and to get uniform distribution over the field. We've made very recently a change to build the hash to base from HKDF. The idea there is to defend ourselves against cases where the hash function underlying that is less than perfect. One thing, and this was a suggestion from Hotek Wee and Sergey Gorbanov, who are working on the BLS signatures, is what we call pre-hash for free. The idea here is hash to base is designed in such a way that no matter what you do, you only have to pass over the input string once. So what this means is that if an invoking protocol forgets to or doesn't want to define a pre-hash mode, that's okay. You can still get the efficiency of only passing over the input once. And finally, we've recently added domain separation guidelines. Domain separation in general is not a magic bullet, but it can save you, and it can be useful in proving properties about sort of compositions of protocols. So our hope is that people will use it proactively, and we give some guidelines for how to do that. As far as the maps, this is sort of the bread and butter of the hash to curve. This is where all the algebra is. A few things that we've done in this draft. One, we specify how to choose the sign of the resulting point. This is different than what was going on before, and the goal here is we don't want to have to tell implementers this is the way you must compute square root, because of course square root can give you 2 possible values. Implement it however you want. You will still be able to interoperate with other people as long as you fix the sign up at the end. We've explicitly handled all the exceptional cases, or at least that's the intention. Perhaps there are some that we missed, but if we have, please bring that to our attention. We've removed the SWU algorithm in favor of a generalized version of the simplified SWU. So the simplified version is faster, and it covers now all the same curves. Let's talk about IPR to the end, because there may be something there. We've also unified the way that Alligator 2 is done for the Montgomery and Edwards curves. The goal here is if somebody is implementing something over, say, curve 25519, it'll be possible to for one implementation to work on the Edwards curve and another implementation to work on the Montgomery curve, and that's okay. You can still arrive at the same answer in an efficient way. And finally, we've added a new map for pairing friendly and some other curves based on some work that Dan Bonet and I will present at Chess in about a month. Not much to talk about in clear cofactor, so I'll jump right to the suites. So the idea of suites is we're trying to give people sort of a menu. Like if you just want to, pop into the document, you have your curve already in mind. Here's how to do it. So right now we're specifying suites for the NIST curves, and you can see them on the slide there. And the goal is we're going to provide for all of these suites sort of constant time optimized pseudocode. And of course, constant time with the proviso that all the underlying primitives are constant time. That's out of scope for the document. So for example, we're not going to tell you how to do constant time multiplication because you know that better than I do, certainly. But the assumption is as long as you have those, the result will be constant time. We're going to, like I said, we're going to give that for all the suites. There are some other planned additions. So one thing we need to do is cover more curves. We'll certainly cover all the curves from the pairing-friendly drafts because that's a place where people really tend to need hash to curve. And another thing that we're considering is sort of a way of helping people to sort of choose the suite that we would have chosen if we were thinking about the curve that you're thinking about, but we didn't think about for some reason. So that brings us to the kind of open questions. A couple that I have are there any curves that people want to see covered that aren't currently? Specific question, are there any super singular curves that people care about? We could imagine putting some in just for funds, perhaps like seaside related curves. But as far as we can tell, there isn't much going on that actually has a lot of use of this. So not obvious that we should be incorporating it. IPR concerns, this is going to become a big thing, I'm sure. So it appears that the ECART algorithm is covered by, look, I'm not a patent lawyer, so this is only, I'm reporting what Bjorn Hasse has talked about on the list. Thank him, by the way, for good work there. So ECART appears to be covered by a patent. Simplified SWU also appears to be mentioned in a patent, but in a much narrower way, again, with the proviso that I'm nothing like a lawyer. So we need some fallback solution. One possibility is to bring back SWU. And we've talked about this on the list. I have an alternative proposal, which is to use the sort of the shallow and Van de Woestijn map, which is what underlies, that's the S and the W in SWU. So sorry to Ulas, we're not trying to kick you out. The idea is it's possible actually to get an even more general map than SWU with essentially the same performance and actually a simpler interface. So whereas SWU kind of breaks the abstraction that we're trying to build for map to curve, shallow and Van de Woestijn, works with the same interface. So from our perspective, it's strictly better, but of course we want to hear your feedback on that. So at this point, I'd love to hear any feedback, anything that we're not covering right now, any bugs in the document. Actually, thank you, Dan Harkins, who has already pointed out some bugs in the document. It's getting better. Thank you.
Okay, all right, thanks, Rad. And let's move on to the PIG update.
Yeah, just very quick question. So are you thinking it's one more revision, couple of revisions before last call, or?
It certainly depends on how we count revisions. Okay. I mean, we can probably crush it all into one. Yeah, in principle,
it's pretty close, basically.
It seems like it's pretty close. There's organizational concerns and clarity concerns that we're learning about, and we have to cover a few more curves, but I don't think there are huge changes coming.
Okay. Excellent. Thank you. So, yeah.
So Stanisław Smyszlejew again, now as Cfrg secretary. So we have this ongoing process of PEG selection process, and I'd like to give an overview of our current status. So it all started at IETF 103 when there was a decision to start the process, to involve crypto review panel to come up with recommendations, and when there was a decision to try to select 0 or more or 1 or more PEGs to recommend to the community. So we have the following timeline. On stage 1, we had our call for candidates and first round of discussions of the list of questions to be asked. And on stage 2, we collected the responses from the designers of the protocols for all positions of RFC 8125 with the requirements for PEGs and all additional questions that we collected at stage 1. Now we have 4 stages in the future, and these stages are about reviewing. First of all, we'll have a call for reviewers for the enumerated questions, because some of them are not about the security assessment, and so they are better to be done not by criteria panel members, but by independent people who know a lot of particular stuff related to these questions. Then the reviewers make their analysis, and then criteria panel members provide overall reviews for each candidate. And in the end, Cfrg chairs discuss the reviews and try to make some recommendations, and if they're ready to make some recommendations, then at IETF 106, some packs are selected, and a production of a document like recommendations for password authenticated key agreement in IETF protocols are established with reflection of the results of the selection and some important recommendations for applications. And at the same time, documents and usage of the specs in the protocols can be developed. So what we have now? We have very good list of nominations. We have 8 nominations, 4 for balanced, 4 for augmented, and these are really strong candidates. I think we are very in a good position now here. On stage 1, we also collected a number of questions to be asked. They are about huge requirements, about crypto agility, about applications of PAC, about performance, about security assessment, about security proof, and about recommendations for secure usage. The last one is very important because a lot of PACs can be broken because of very small problems with implementation. So this kind of questions is really important. On stage 2, we collected the responses from all the authors, and many thanks to all authors to providing their responses in time. And there was responses for requirements of RFC 8125 and the opinions and the questions collected at stage 1. So the responses for all 8 protocols. What's next? So now we are starting to do the reviews, and the current stage, which may be the most important one, is about call for independent reviewers for specific questions that we have. First of all, 2 questions that, in my opinion, are the most complicated ones are about integration of each PAC candidate into TLS 1.3 handshake and into IQ2. About TLS 1.3, we had a lot of drafts, documents, and discussions. And earlier at IETF 104, I made a presentation in Prague with some overview of existing documents. And we must take all this into account, and we really need people who really know TLS and can prepare their reviews and spend some time for reviewing each PACs, considering regarding the usage with TLS. And the same thing with IQ2. I know that there are some experimental draft about usage, experimental RFC about usage of PACs in IQ2, but I think that a lot of questions will be raised. And also there are questions about usage in IoT. So when we have at least some limitations on hardware and maybe additional limitations on round efficiency, and about privacy, at least about recommendations to prevent user enumeration in some protocols. For example, in OSpace and in OPEC, we have explicit recommendations about this, and this is a question that also has to be verified. So, in fact, the main purpose of the slides was not only to give the overview, but to announce the call for viewers. I think we'll repeat this on the list. And we really need the reviewers for the questions, because I believe that crypto review panel members will provide really good security assessment, really good verification of all security proofs, but it will be really good if people who know each piece of TLS and a piece of IQ2 could assess each PAC regarding their convenience to use it for usage with these protocols. So that's all. Please, questions, and please, we really need help here.
Hello. Maybe one formal remark for the process of finding independent reviewers. Main questions belong to interoperability with TLS and IPsec. Based on my experience in ITU, in that case, you use some kind of liaison statements to request people from these groups. I hope that the people from TLS and IPsec are here, but it can be not the case, or not such so much people, so many of them here. I propose to ask corresponding working groups and working group chairs to assist in finding independent reviewers from the people working in these groups. Thank you.
I think that we'll have the comment, yes, or the question.
We certainly have people who are experts in TLS in this room, so
yes.
staring at some of them.
Yeah, and the IKE people too.
Yeah. And we did announce in the TLS working group at least that this competition was going on and that we needed reviewers.
Relaying from Jabba. Jorn, I don't know, says, could you post a place where to find the replies regarding VTBPEKE? I did not find it on the mailing list.
Sorry, could you repeat it?
One of the texts did we have
could you post the replies regarding, I'm not even going to try, VTBPEKE?
Of course, there was replies about VTBPEKE and it was collected and it was on the slides. So yes, for all protocols, including this VTBPEKE, we have the responses and yes, we've collected them, so no problem here.
Are they published somewhere?
They was sent, some of them was sent in the list, some of them was sent directly to the chairs. So I think that on stage 3 or stage 4, we just publish all the stuff that we collected, because some answers was not in the single message, some were in the PDF. So we'll try to organize this in some case, in some sense, and publish it for reviewers in a convenient way.
Yeah, collecting all the responses in one place would be a good idea.
Yes,
right?
we'll do this, but the responses even was obtained after the deadline, if to be honest, some responses. So we'll integrate them into 8 groups and have this ready for the reviews.
Sorry, I have an is typing here, so I'm just waiting to see if anything comes up.
So
nothing. Okay.
All right. Okay. So, and if you have any other considerations about the process and any other questions to be asked, please tell at least the chairs, because I think that all new questions can also be considered by the crypto review panel reviewers, like Alexei said in his beginning in the chair slides. So all new questions are still welcome, I think.
Okay, thank you. And a reminder to the group that we are soliciting more participants for the crypto review panel. We expect this review of PIGs for the reviewers to review multiple PIGs rather than one, so that we have a consistent comparable review. We may gather them in respect to augmented, all 4 augmented. Well, we have 4 of each, so it may be 4 per reviewer. So this is quite a large request, and so we would hope we have some dedicated people that have the energy and time to put into this. So we'd appreciate emailing CFRG chairs at IRTF.org.
Okay, thank you.
And by some miracle, we were 10 minutes late. We actually have 2 minutes left. So any other business? 1 minute left. Yes. No, that's great.
Okay, thank you.
Has anybody not signed the blue sheets? Can you come to the front and so we can get even bigger room next time, please?